Today we are going to see the constitutive equations of all the elements that compose the bond graph language, or this set of 9 elements that we had introduced on the previous video. And we are going to study the constitutive laws of each one of them. So on the screen you see the resistive element, which is like a damper or a resistor on an electrical system, or a valve on a hydraulic system. So let's examine in detail each one of them. So in here will disappear. Okay, on the R element in here, for example, you have a constitutive equation that says that the effort is equal to the R times the flow in here. But in order to make some sense of this, I would perhaps take advantage that I can write here, and I would say, for example, on a resistor here, that you have this voltage here across the resistor. This voltage across the resistor is the current times the resistance, you see? This voltage is the so-called effort variable. And then this I is the flow variable, and then there's R. So you see this equation now is exactly like what's in here, see? So this could be true also on a mechanical system example. Let's see if we have a damper like this, where the force is equal to the constant times the velocity. And what happens here is that the force is the effort, then B is the constant here. We're going to B times the velocity is the flow, or this represents the resistive element constant, which would be R times F, which is again is exactly the same equation. Okay? When you write it like this, the fact that you write this equation here, you are saying that this is the output and this is the input. Okay, and this of course is the constant of the element. That is indicated by this little picture here. See, this is your effort here, and the green is the flow. So it means that from the R element, this is what's coming out, this effort, and what's going into the element is this flow. See? So the little picture, when you see R like this, it means this is the effort that comes out of the R, and this is the flow that goes into the R. When you write it like this, the reverse is true, because the output of R is F, and the input to R is E, based on this. Just think as if this would be a piston that you are holding in your hand. Let's see, there you have your hand, like that, and you are pressing it this way. You see, then it would make sense, this plot with something real. So that you can see that the output of R is this flow. So, you know, F could be written here and E could be written over here to make it a little easier to read. But nevertheless, the equation follows here that the output is F, in this case 1 over R times the effort. Okay, so those are the two forms that we have in writing the differential equations, writing the constitutive equations for the element. So in here, you see, if the effort is in times 1 over r, you have the flow. That's what this is. And here you have this. But if you have a, let's see if we could change the pen color. Let's try this to see if this could be easier to write. You see, this is input, and this is the output. So if you were to write, let's say this is R, yeah? What's the output of this? You immediately put F in here. What's the input of this? This is E. That's how this represents this. And the opposite is true on this case. In this case, if you put the R element and you say the output of this is E, then you have this joint, see? You have, this is the effort, which is the output, this is the flow, which is the input. So that is then the C element, which we call the capacitive element. In this particular case, you have a relationship between the effort and the displacement, the generalized displacement. So the constitutive equation would be like this. So if we want to relate this to a physical element, perhaps we can write it down in here like this. Red will still holds okay. Isn't it true that the voltage here is, here the voltage across the C is 1 over C times the integral of I dt, right? Or you could say this is 1 over C times Q. You see, this equation that you see here has this form. See? And that relates directly to a physical element. In the case of a mechanical system, same thing is true. Let's see, to make it interesting, we could just change the color here. Let's see how it goes. Maybe it didn't. Let's say if you have a spring here, a mechanical one, yeah, you write that F is equal to K times the displacement X. This is the same thing as writing E is equal to the constant in here. K is like 1 over C, and then C is the capacitance, so K is the stiffness, so it's 1 over C is K, and this would be the displacement, which would be 1 over C times Q. This equation, in fact, has the same as this. The point is that this, depending on how the equation is written, either you're going to have this form or you will have this other form. In this case, if the flow is the input and the output is E, then it follows that the output, you write always output is 1 over C times the integral of f dt, see? And that would be this form, is called the integral form. But if you write the equation in another way, you can write it in the derivative form, and then you will have that F, this is the output in here, is C times d dt, which would be the opposite of writing this equation. Yeah. So F is C times d dt. That's the same thing as dq dt. And you see in here the objective is to write the derivative in this case. See, this is a nice expression, explicit expression. This one not so nice because the derivative, you get another derivative on the right hand side. But that's what the C element is like. And then we can write this way. You say that the flow is the input, and then you know, if the flow is the input in here, this is input, this is the output. So it's 1 over C times the integral of I dt, which is 1 over S. Mm. And then obtain E sub 4. So that's the C element. Now we could consider the I element, which we are calling the inertia element. And this element will store kinetic energy as opposed to the C element that stores potential energy. The two equations that are possible for this element are written there on the left hand side. In this case, you have that the flow is the output, and on the right hand side the effort is the output. Just think about a moving mass under a force in here. Normally we write the summation of the forces equals to the rate of change of momentum, right? Or m times the acceleration. Huh? Or you could say this is obviously written in derivative form, you see? This equation corresponds to this form because you can see F is E and this is M, we're going to call it I times df dt. See? This form that you're seeing here is exactly what you're seeing here. Yeah? But you could write this in the integral form. So instead of the output, the flow is the input. And if that's the case, you have 1 over I, the integral of E dt is 1 over I times the momentum. If you have this equation here, and we don't want to have it in terms of the derivative form, you see, you can write, if you have it here, that E is equal to I times df dt, what you have to do is integrate both sides. Yeah? So it's very obvious. You could write down, you integrate this with, you would have that this derivative. You can write down that this is 1 over I times the integral of e dt. This is equal to f. This is the same thing as this equation. So the way you orient this symbol is directly related to the form of writing the equations. This was in integral form. This other one in derivative form. So you have to see which one you're dealing with. There's two possibilities. And of course, if you put it in the terms of the block diagram, the symbol would be as is shown here. Because you see here, this is your output. And this is your input. And that's how you write it, because the output you're seeing here is this is your input. All right. So you have 1 over items and the integral, and then see this is being written like this, that f sub 4 is 1 over I, the integral of e dt. This equation that you see written in this form is what is represented on this picture. Okay, let's just move on to, there's two kinds of sources. There is an effort source and a flow source. And in here you have on the left hand side, an effort source, like you can see, is like a voltage source. And on the right hand side, you have the velocity source. Let's say when you're going the suspension of a vehicle following the terrain, this is a velocity source, not a force source. The reason is that the wheel is forced to follow the ground, and therefore you have an input source, a velocity source. You could write it like this. Either you have this, you could write it like this, where the effort is the output, and you could write like this, source of flow, if the effort is the input. So you see here is, you could say this is the force, right? And this right here is the velocity. So this is like you're saying that it goes from source to the system. So in here you go on for the other one. In here, this is originates. This is a flow. See, and this is the effort, like that. This is the reverse. The flow source provides a velocity input, and the effort source provides a force input. In the case of an electrical system, the flow source would determine the current. and then the AC would be a voltage source. Okay, you can several ways to represent the um, flow source. I mean the flow source and the effort source. There's only one possibility. If it is an effort source, it has to be behave like this. From this to the system, and from the system to this, yeah, this is the flow output, flow input, effort output. This is the opposite. This is like your velocity source. The other one was like a force or voltage. Okay, so those are the two elements, the flow source and the effort source. Now there are two elements that we call two-port elements, and you can see they are very well indicated on these two pictures. The one on the left-hand side is a lever, and it's very obvious that in here you could say that you multiply the force F times A. See here, if you say F1 times A should be the same as F sub 2 times B. From this equation, it follows that F1 multiplied by A over B should be F2. This equation that you see here okay, so that's as far as concerned. This is another kind. So you could write this like this. See, you have a transformer here, and on this side you have F1, and then you have A, and then you have this F2. But the modulus of this is going to be A over B. Okay, the opposite is true on this. You see here you have the force is going to be A2 over A1 times P. Okay, so this again, you have this would be TF, where this would be the modulus in here would be A2 over A1, and then this would be F, and then P on this side. Okay, so you have the two transformers. I mean the two possibilities for the transformation. We're gonna see it on the next slide. You can see this is depends on how you write the equations for the system. Either take this form or will take this form, depending on how the equations are written. This is another illustration of what it would be in a block diagram, but the picture on the right hand side would be in a block diagram. So the way you read this is, you read it like, if we read it from here to there, what's the input? Is F4. What is the output? And then you have the other possibility. See, so 4 is the output. See, this is how you should read. This is out, and this is out too. This is in. So what happens is you read from here to here that E sub 4 times this modulus. So E4, let me write down very well here. E4 times E4 times the constant here is equal to E sub 5. No, but you see, this is not the way it's. This is not the way it's written. We need to do a better job. If this is the output, it follows that E sub 4 has to be the input times something, and this is E4. The way you read is E4 is E5 times the modulus here, M. So, and then the output is going to be F sub 5 is going to be F sub 4 times M, which is the input here, is equal to F sub 5. So that's how we write the equation here. The way we write the equation here would be the way it's written here is the output on this side is the flow, and this is the input here, F sub 4. These equations are the equations that you see here. This would be E sub 5, F sub 5. Alright, here's the other form. So you could have, if the modulus is written in terms of the output F or 5 or the flow 5, flow 4 in this case. So how would this be on this? The equations here says E sub 5 is equal to 1 over T transformer for 5 times so that's the TF element. We have one more. This is the gyrator element. The gyrator element is, as you can see here, this is like a cross transformer. The electric motor is a perfect example because you write the equation in here. The relationship between the output is directly related to the to the RPM of the motor, or the current is related to the torque. That's how this works. So this element has the same kind of properties as the transformer, but the variables are crossed. Like you relate, instead like on the transformer, we relate one effort to another effort or one flow to another flow. That doesn't happen on the generator. This is, you can see clearly this is a velocity here and this is a force. So it's related that way. Or in here, that the effort is proportional to the R onto omega. Okay. So those are the last elements, and then of course we have the representation of the equations of this generator. As you can see on the screen, you can have the two ends, the efforts towards the end, or the two efforts towards the middle, like in this case. So this is the case where the flow goes in, gets transformed into an effort. The other one is you're studying this GY element, and we want to write the equation of motions is to look at what's the output. And so we have either these equations or we have these equations. What's not possible is something like this that looks like a transformer. This no, and this too not possible. But the other two up there are fine. This is a, we call it a cross transformer because it crosses the lines on both directions. Like the effort in this case comes in, gets transformed into a flow. You see? The other one from here, effort, then multiplied, then you're gonna have E sub 5, F sub 5. This is the other kind. So in this case, do you notice what the input is for to the G? This is in. This is out. But you see, this is also an in. And this is an out. I don't like the way it's written here, so let's just write it in here, output. And that's how we write the equations. The equations are directly related to this block diagram. In fact, I always have said that the block diagram is just a representation of equations. Okay, finally, we need two junction elements. We need to connect these elements that we have seen. You have this the zero junction here, which is this type of connections that you see on the left hand side, where you see the flow goes in this way, another flow goes in this way, and another one continues like that. This is a, here you know the flows, they sum, but this is a constant pressure, right? like in this case, constant P, constant pressure. So you add the flows, but the pressure is the same. In fact, what Pascal principle says that, right? It says that if a fluid is pressurized and it goes several, you may say, pipes that connect, like in this case, that the pressure is the same all over. That's how the principle of the brakes on your car works. Huh? And on the other hand, on the right hand side over here, you can see this node in here that you see. Let me just draw it separately. It's here you have I1. I2 continues like that. But this one is I1 minus I sub 2. Yeah? And that's what you're seeing here, see? The way you represent this is you say this is a 0 with this, and this. That's how we represent this kind of connections. And we only have to go one more, which is the one junction. But before we do that, this is another representation of the equations now that correspond to the bond graph model. All the efforts the same, but the flows will add up to 0. And then we have different possibilities for this power flow and the 0 junction. So you can have the possibility of this equation here. The half arrows are determining how things sound. That's what we need for this. Like in this case, you see, I'll repeat it over here. This comes in like that. This other one comes like this. So the result is this. Okay? Result. And in here, you see all of them going out. One way that you can adopt this summation convention, you may say, is all the flows at efforts constant. Or what comes in is positive, what goes out is negative. That works too, as long as you are consistent. In this case, see all two come in, one goes out, but the efforts are the same. But if we put the causal marks, one of the things that we really need to emphasize is that only one of the bonds would set the effort to all the others, or set the flow for all the others, but in this case, the effort. So you say this is the effort here. So it comes from some place in the system over here, this way. This is the input. And therefore, the other ones have to be out, like this. Yeah, and this has to be out, like that. If you do it this way, this sets the effort, and the other ones have to be out. This one, they set this one, the others have to be out. So there's always the interaction between effort and flow in every system, in any domain. And I have put both of those, the causal marks plus the half arrows, in this picture. The common effort junction, all bonds attached, all effort are the same. The sum of the flows equals to 0. It's power conserving, powering equals to power out. Only one causal mark determines the input effort, and all other efforts will have to be outputs. There can only be one and only one bond that sets the effort input. And finally, power flow and the errors are determined how the flows will sum. The last component of those 9 is the one junction. The one junction, as you can see in the picture on the left-hand side, means a common flow. This is a common flow junction. That means you can have in here, this flow is the same, and you could actually build the system like around this. You say constant flow, and in here, this is my R element. This would be the C element, and I have in here my voltage. Yeah. So in this case, you have the voltage. This is like this. And then you have this would be the constitutive relationship for the C element. Then obviously this one will have to be the one like this. On this other one over here, this again, the velocity is the same for all the members of the connection, this junction, but the forces will sum. So if you represent it in this picture, you could represent it by F1 equals to F2 equals to F3, while the efforts will add up to 0. And if we do it just like we did for the zero junction, we could examine several possibilities depending on how those arrows come in, depending on how this comes in here and what goes out. We write the equations. Same thing here. This two coming in and this one going out. So the flow is the same, but what we add are the efforts here. And then finally we have this one. You have, just for the sake of example, I put all of them out, and that's how this equation will be. So I think it has worked out for me just to make it positive when it's in, negative out, and then you can write this equation correctly. Same thing true for the one on the right hand side. Different possibilities for the one junction. One junction has only one flow in. All the others flow out. See, one flow in, the others out. One flow in, the others out. Okay, can only have one flow in. And in here, there's the same cases as we presented for the zero junction, but for the flow, in this case, all flows are the same, but the efforts will add up, will sum. And how do we represent this into a block diagram? Yeah, this is the symbols using in Simulink, or we use a circle too. The summation points you could use with a circle here, where you say the output of this is E sub 4, and then you have in here E1. Well, actually, we will have to write it like this. And then you have E sub 2. Oh, 4 yes now. There's, see, this is the same way. The same way over here. In this case, what's the output? 4 input 2, and this goes to okay. So with this we conclude all the properties of the one junction. It's a common flow junction. All bonds are attached, all flows are equal. The sum of the efforts equal to 0. It's power conserving. Power in equals to power out. Only one causal mark determines the flow. And there can only be only one bond that sets the flow for all the others. Power flow half arrows determine how the efforts will sum. Okay, so this concludes the summary of all the constitutive laws of all the 9 elements.